Hi, I Smutara Reshma from University of Toulouse, France, would like to present our paper entitled Natural versus Balanced Distribution in Deep Learning on Whole Slide Images for Cancer Detection. Here is our presentation outline. First of all, I would like to talk about the background and motivation of this research. This is a domain-specific studies, and the domain is cancer detection in histological images. Here are the steps in a manual cancer detection system. In a manual cancer detection system, pathologists collect tissue sample from the patient. Then they do sectioning and staining to give contrast of color to the tissue sample. Then send it to the scanner to produce digital image, which is called whole slide image. From here, pathologists find cancer affected area by looking into it, which is time consuming. Moreover, pathologists might misinterpret or overlook small cancer affected area. In this regard, computer aided cancer detection system could be a great help in reducing or eliminating the limitation. Here is an abstract computer aided cancer detection system where the whole slide images and their annotated masks are used to train a deep neural network model, and the trained model is then used to predict the annotation of an unseen whole slide image. However, the performance of the system depends on some factors, for example, neural network architecture, optimizer, loss function, training data, etc. In this research, we focus on training data. There are some problems in using whole slide images as training data. For example, they are very large in size, usually gigapixel. Since they are large, pixel level annotation is costly. The distribution of pixel class is not balanced, and there are interclass similarity and interclass difference which cause false positive. In this slide, I would like to discuss about the WSI or whole slide images as training data. Here is an example of whole slide image of metastatic lymph node with its annotation. Here each color represents a class. The red color represents cancer class, blue represents non-cancer class, and gray represents other class, which is mainly background and histological structure other than lymph node. However, the lymph node is the region where pathologists look for abnormalities. Thus, it is the region of interest or ROI, and the remaining are the non-ROIs. In a whole slide image dataset, on average 70 to 80% are non-ROI pixels, and common practice is filtering out non-ROI and adopting balanced distribution for further processing. Thus, the original or natural distribution and non-ROIs are yet to be explored. In this paper, we are exploring those. The importance of the exploration lies in false positive issue of the state of the art. In state of the art, false positive issue is still unsolved, and one of the reasons of false positive is interclass similarities and interclass difference. Now I'd like to present a short review of related work and their limitation. In literature, there are hundreds of studies in different domains supporting balanced distribution and proposing method to achieve it. Among them, some support data level modification, for example, oversampling, undersampling. Some support algorithm level modification, for example, modifying or proposing cost function, and some supporting hybrid method of data and algorithm level. There are some comparative studies among different methods of making balanced data distribution. For example, Buddha et al. Support oversampling, while other study claims that there is no evidence that a particular method is superior over other. All these studies consider imbalanced distribution as disadvantageous for classification and propose a method to make the data distribution balanced. However, the comparative studies among different distributions are very few, and they are done on toy dataset. Among the existing studies, Some support natural distribution, some support balanced distribution. That means the outcome of the studies are inconsistent. Thus, separate domain-specific studies are required. Zhu et al. Did a domain-specific study on land cover data. However, there is no study on the domain of cancer detection in whole slide image data. Here I list up the limitation of the related work that we mentioned in previous slide. In the related work of cancer detection in whole slide image data, almost all of the study present a end-to-end pipeline where filtering out non-ROI and adopting balanced distribution is common. Thus, original data distribution and non-ROI are yet to be explored. Ours is aiming to exploring those. Now I would like to discuss our methodology. To explore the natural distribution and non-ROIs, we designed two experiments. Experiment A for balanced distribution and experiment B for natural distribution. We total nine units of example in each experiment. The number of example in a unit depends on two factors. They are the size of smallest class and its largest presence in an expected ratio. For example, if class C is the smallest class and its largest presence in a ratio is 3, then 1 unit equal to n by 3, where n is the size of class C. Moreover, since learning is a stochastic process and one run per experiment might not be enough to test some hypothesis, thus we consider 10 runs per experiment. Here is our working framework. We have training whole slide images and their annotated mask. In the pre-processing step, we extract overlapping patches from the training data, then categorize them according to the pixel classes they belong to. Here we categorize them into 4 categories: the non-ROI or class O patch, cancer patch, non-cancer patch, and the mixed patch. In the training stage, we select patches of the different categories, thus create different distribution of the classes and train a deep model. In the testing stage, the trained models are used to predict the annotation of the unseen whole slide images. In particular, we extract overlapping patches by maintaining a particular stride and predict the confidence score of each pixel for each class. From the predicted score, we consider the middle portion, which we call the center region or CR, for further processing. In the evaluation step, we consider both single threshold-based metric and multiple threshold-based metric. Thus, we post-process the predicted score in 2 different ways. For single threshold case, we consider the default arithmetic decision of the model and find the class level of each patch. On the other hand, for multiple threshold case, we require predicted score of class C for each patch, and we consider the maximum score of center region as the score of the whole patch. Here is our hyperparameter setting. We consider popular UNet as a network architecture, which was implemented using Keras with TensorFlow backend. The loss function was categorical cross entropy. Optimizer was Adam with learning rate 1exp -5. In the selected training subset, we consider 80% for training and 20% for validation. The size of the structured patches was 384 by 384 pixels. The pixel values were scaled up in between 0.0 to 1.0. The number of maximum epoch was 35 and minibase size was 5. For further information regarding this, I would like to invite interested reader to read our paper. As dataset, we used a metastatic lymph node dataset from the University Cancer Institute Toulouse Oncopole, which is called MLNTU dataset. In the dataset, the whole slide images were stained with hematoxylin and leucine. The dataset contains 16 primary cancer types, and the ground truth masks were annotated with 3 classes: metastasis cancer class, lymph node or non-cancer class, and background or other class. In the training set, it contained 34 whole slide images with their ground truth mask. In the test set, it contained 27 whole slide images with their ground truth mask. Here I also present the pixel distribution in the training and test set of the MLNTU dataset. And we can see that most of the pixels belongs to the non-ROY class O, where two other class distribution could be balanced or imbalanced depending on the included whole slide images in the dataset. In this slide, I present the statistics of the extracted patches from the MLNTU dataset. From its training set, we extract total 128K patches, where around 90K belongs to non-ROY class O, around 15K belongs to cancer class C, and 17K belongs to non-cancer class not C, and around 5K belongs to mixed patches. According to the formula defined earlier, 1 unit equal to 5K and the size of the training subset is 45K. In the test set, total number of extracted patches is around 100K, where around 17K belongs to cancer class. Here is our evaluation matrix. We considered well-known accuracy, precision, recall, and F1 measure as single threshold based evaluation metric, and receiver operating characteristics or ROC curve and precision recall or PR curve as multi-threshold evaluation metric. Here is our evaluation result in terms of single threshold based metric. In the figure, the height of the bar represents the mean performance of the 10 runs, and the black line segment represent the standard deviation. We can see that experiment B, that means the experiment with natural distribution, gives the better accuracy and precision than the experiment A, that means than the experiment for balanced distribution. While in terms of recall, the result is opposite. However, while considering recall precision at the same time, that means while considering F measure, experiment B gives slightly better result than experiment A. In terms of precision, around 7% high precision for experiment B than for the experiment A indicate that experiment B producing less false positive than experiment A. We also investigate the reason of having lower recall in experiment B, and we found that it is due to not using all the cancer patches in the training set of experiment B. To have equal number of training example in both experiment, we undersample the cancer patches in experiment B, while in experiment A, all the cancer patches were used. Thus, having less recall in experiment B is normal. These results are for multi-threshold based matrix. Here, the blue curve are for the experiment B, that means for the experiment with natural distribution, and the green curves are for the experiment A, that means for the experiment with the balanced distribution. While the corresponding color shading represent the standard deviation. We can see that blue curve is better than the green curve in terms of both ROC and PR curve for almost all threshold points. That means experiment with natural distribution is better than the experiment with balanced distribution. Here we present an example prediction for one of the most false positive generative whole slide image in the test set, and we can see that experiment B is producing less false positive than experiment A. Here we present an example prediction for a micrometastasis whole slide image, and the result is the same. The experiment B is producing less false positive than experiment A. This example for a full negative whole slide image, and the result is also the same. Experiment B is producing less false positive than experiment A. We further investigate the reason of producing false positive by manually looking into the predicted mask. During investigation, we found that our initial hypothesis is true. That means interclass similar region are producing the false positive. Here are some examples of interclass similarities between the cancer class C and non-cancer class O. In the top row, The patches are cancer class examples. In bottom row, the patches are the non-cancer, non-ROI or class O examples. We can see that in first column, both classes contain fluid. In second column, both contain blood. In third column, both contain fibrosis with lymphocyte. Thus, if there are not enough examples of non-ROI class O, all the interclass similar region of class O would be predicted as class C as false positive. Overall, naturally biased towards the non-ROI class produce better performance than balanced distribution for cancer detection regarding the false positive generation, yet maintaining a comparable sensitivity or recall. In other words, non-ROIs are useful. The concluding remark is, here we provide a new viewpoint regarding the natural distribution and the non-ROI in building a training data for cancer detection. However, in some regard, our work is limited because we only consider the natural and balanced distributions. In future work, we would like to observe the impact of other distribution, for example, lymph node biased or cancer biased distribution. Moreover, the usability of the mixed patches are not explored yet, which would be another compelling track to investigate. Thank you very much for your kind attention.